What is a polymer? Polymers, or macromolecules, are an incredibly diverse group of large molecules that are composed of repeated subunits called monomers, which are represented here by the blue circles. These monomers join together to form chains that can be as short as just 2 or 3 monomers, called a dimer or a trimer respectively, or as long as hundreds or even thousands of monomers. Both natural and synthetic polymers exist, with a range of properties and applications. Nylons are a group of synthetic polymers, one of which, nylon 6, is shown here. Nylon 6 is used in a range of areas, including in synthetic fibers for clothing, in the frames of some modern firearms, and in surgical sutures. Polyvinyl chloride, or PVC, is another, which is commonly used in water pipes, flooring, and as an insulator for electrical cables. A third example is Kevlar, a very strong polymer with useful thermal properties that is used in ballistic vests, brake pads, and even in some canoes. Natural polymers, or biomacromolecules, include proteins, which are macromolecules composed of amino acid monomers, and polysaccharides, such as starch, cellulose, or glycogen, which are made from sugar monomers. DNA is also a biomacromolecule, the backbone of which is composed of repeated nucleotide subunits. Polymers can grow via two main mechanisms, chain growth and step growth. In chain growth polymerization, only the end of the growing polymer chain is reactive, and so the monomers are added one by one. In contrast, in step growth polymerization, both the monomers and the growing chains are reactive, and so chains can react not only with monomers, but also with other chains. These two contrasting mechanisms have very different kinetics. In chain growth polymerization, the length of the chain increases linearly as more of the monomer is converted, which is due to the fact that only one monomer can be added onto the chain at a time. For step growth polymerization, this linear relationship does not exist. Instead, the monomers initially join together to form shorter chains, and as more of the monomer is used up, more reactions occur between existing chains, forming longer, higher weight polymers. Chain growth polymerization reactions have three main stages, and shown here is a mechanism for the free radical polymerization of propene to form polypropene, also known as polypropylene. The first stage of this mechanism is initiation. Here the benzoyl peroxide undergoes homolytic fission in the presence of UV light, producing two benzoyl radicals. These then go on to react with the first propene monomer, opening up the double bond and starting the chain. The product of this reaction is another radical that can react with another monomer, and this step, called propagation, can be repeated numerous times, growing the chain until the final step, termination, occurs. In termination, the reactive end of the chain reacts with something other than a new monomer, forming a non-reactive end group that prevents the polymer from growing further. In this case, the polypropylene reacts with another benzoyl radical initiator, terminating the chain. Many polymerizations involve those same three steps: initiation, propagation, and termination. But what if there was no way for the reaction to terminate? When polymerizations can't terminate, they are known as living polymerizations. In a living polymerization, all of the chains start forming simultaneously, and the reaction continues until all of the monomer has been consumed, which leads to polymers that have very similar chain lengths. The chain length is determined by the ratio of the concentration of the monomer to the concentration of the initiator, so by varying these, the length of the chains can be strictly controlled. Even when all of the monomer has reacted, the end group of each chain is still reactive, so by introducing a second, different monomer after the first has been completely consumed, living polymerizations can be used to produce block copolymers, which are polymers composed of blocks of different monomer species. The ability to include specific amounts of different monomers in the same chain allows macromolecules with very specific and useful properties to be engineered. For example, by building a block copolymer from a block of hydrophobic monomers followed by a block of hydrophilic monomers, amphiphilic polymers can be created. In a process called self-assembly, these amphiphilic macromolecules spontaneously arrange themselves in water to form spherical structures called micelles, which are spheres where the hydrophilic parts of the chains point out into the water, and the hydrophobic parts all point into the center of the micelle in order to minimize electrostatic repulsions. But how does all of this link to medicine? Around 70% of newly synthesized drug candidates are hydrophobic and therefore very poorly soluble in water, which greatly reduces their availability in the body, or bioavailability, meaning that they need to be combined with other compounds in order to be administered. Paclitaxel is one such hydrophobic drug. It is a chemotherapeutic agent used to treat a number of different cancers, including breast, lung, and pancreatic cancers, among others. And due to its hydrophobic nature, it is usually combined with colifor-EL, an emulsifier that allows the drug to be dispersed in a liquid that can then be administered intravenously. However, colifor-EL is not inert and is responsible for many of the side effects associated with paclitaxel. This is where self-assembling amphiphilic block coat polymers are useful. In water, the polymer chains form micelles around the hydrophobic drug molecules, which can then be dispersed in the water. Block coat polymers of gallic acid, chitosan, and TGPS can be used to encapsulate paclitaxel, achieving the same thing as colifor-EL without any of the associated side effects. This polymer also allows it to be administered orally, which is much safer and easier than intravenous administration, and this has been found to increase the bioavailability 3.8-fold, resulting in increased anti-tumor efficacy. The increased bioavailability also means that lower doses of the drug are required to achieve the desired effects. Another potential use of polymers in the administration of paclitaxel is in targeted drug delivery. Paclitaxel works by preventing cell division, which causes cell death, and the effect is greater on cells that reproduce more frequently, such as cancer cells. However, this is a double-edged sword, as whilst it is effective in attacking tumours, paclitaxel cannot exclusively target them, and it also attacks healthy cells that happen to reproduce rapidly, such as blood cells and those in hair follicles, which leads to a number of side effects. By using monomers that change from hydrophobic to hydrophilic in acidic microenvironments found around cancerous tumours, polymers can be designed that will self-assemble to form nanoparticles that encapsulate the drug in the blood, which has a pH of around 7.4, which are then transported to the tumour, where the pH is below the pKa of the hydrophobic monomers, causing them to become hydrophilic. The chain is now no longer amphiphilic, so the micelles disassemble, releasing the drug near the tumour where it is needed. Because the drug is encapsulated until it reaches the tumour, it can't attack healthy cells, thereby reducing the side effects of the paclitaxel. It's safe to say that polymers have a huge role to play in the future of medicine, enabling increases in the safety and efficacy of current drugs, whilst also allowing new drugs to be explored that would previously have been dismissed due to their poor solubility. Thanks for watching.